This lab investigates the inverse square law and polarization properties of light. We all know instinctively that the farther away a light source is, the fainter it becomes. The quantity we detect is the intensity, defined as the power per area. Intensity has units of watts per square meter. Imagine a detector, shown here with a square entrance pupil, placed at distance r from a point source of light. If the distance is increased to 2r, then the same amount of light energy now passes through 4 times the area, and the intensity thus decreases by a factor of 4. Increasing the distance to 3 times the original distance decreases the light intensity by a factor of 9. We call such a rule an inverse square law, and have encountered it previously in the context of both the gravitational and electrical forces. Another way to look at the situation is that the point source radiates its power P uniformly in all directions, such that if we sample the radiation passing through a unit area at a distance r, the intensity is given by the power of the source divided by the entire area of the sphere. Since the area of a sphere is given by 4 pi r squared, the intensity drops off as the inverse square of the radius. A plot of intensity versus r shows the reduction in intensity with increasing distance. Quantitatively, we can write that the ratio of the intensities at 2 locations is equal to the inverse square of the ratio of the 2 distances. Thus, if we double the distance from the source, we can expect the intensity to decrease by a factor of 1/4. Tripling the distance leads to a decrease in the intensity by a factor of 1/9. A plot of intensity versus the inverse square of the distance is expected to yield a straight line. Another way to express the inverse square relation is to state that intensity is proportional to distance raised to the -2nd power. We take the logarithm of both sides to transfer the -2 from the exponent to become a multiplying factor of the log of r. We now find that the log of I is linearly related to the log of r, and that the slope of the linear relation is -2. Thus a plot of log I versus log r is expected to yield a straight line with a slope of -2. Our light detector in this experiment will be a light-emitting diode, or LED. Normally an LED emits light when connected to a voltage source. Here, however, we use the LED in reverse as a photocell rather than a light emitter. When connected to a voltmeter, the LED produces a voltage proportional to the light intensity. The LED may be either placed in a copper sleeve and held in the 3-finger clamp, or mounted in an aluminum rod for ease of use. Begin by making sure that the 100-watt bulb is centered over the 0 centimeter mark on the optical bench. Also check from a bird's eye view that it is centered over the bench laterally. Place an aperture hole close to the bulb, at the same level as the bulb and in line with the optical bench. This small hole makes the light bulb more like a point source of light. Place the LED facing the bulb at the same height as both the bulb and the aperture. Use alligator clips to attach the voltmeter. From now on, we will use the term intensity when referring to the voltage reading, since they are proportional. With the background lights low, use a white card to adjust the light from the bulb so that it always falls on the LED detector over its entire range of distances. Now read the intensity, i.e. voltage, at distances of 20, 25, 30, etc. centimeters. Cover the aperture hole and take a reading of the background intensity to be subtracted from all other readings. A plot of intensity versus distance shows the inverse square law. Fit the curve a times x raised to the b power and determine the parameter b. We expect a value of b close to -2. Plot intensity versus 1 over r squared. This is expected to be a straight line. The correlation coefficient will indicate how nearly straight the data is. Remember that plotting the log of intensity versus the log of distance is expected to be linear with a slope of -2. Here is what the log-log graph might look like. You will now apply the inverse square law to determine the luminosity or power output of the sun in watts. From your time at Guantanamo Bay or other tropical climates, you will have experienced the power of the midday sun. Place your hand near a 100-watt bulb to try to recreate the same intensity as a hot summer day, and measure the distance between your hand and the bulb. By equating the intensity of the sun with the intensity of the bulb and applying the inverse square law, we can determine the power output of the sun. Since the distance to the sun is much larger than the distance to the light bulb, we expect the power output from the sun to be many times larger than the power output of a light bulb. In practice, it is easiest to place your hand with the light bulb on, then turn off the bulb for the distance measurement, keeping your hand in place. Be sure to measure from the center of the bulb, not the surface. We will now explore the effects of Polaroids on light. Visible light is a small fraction of the electromagnetic spectrum. Electromagnetic waves consist of oscillating electric and magnetic fields traveling at the speed of light. As with most waves, the energy carried by the wave is proportional to the square of the amplitude of the wave. For electromagnetic waves, this means that the intensity of the wave is proportional to the square of the amplitude of the oscillating electric field. Light produced by the bulb is unpolarized. That is, it consists of equal portions of vertically and horizontally oscillating electric fields as shown in red on the left. After passing through a Polaroid, with its transmission axis oriented vertically, only vertically polarized light remains, with the electric field vector oscillating in the vertical plane. When this vertically polarized light with amplitude E0 passes through a second Polaroid with transmission axis tilted by theta degrees with respect to the first Polaroid, only the component of the electric field along this new axis direction is transmitted. The amplitude of the electric field is thus reduced to E0 cosine theta. Since the intensity of the radiation depends on the square of the electric field amplitude, the intensity is reduced by a factor of cosine theta squared. This rule is called the law of Malus. Note that when the two Polaroids are aligned parallel such that the angle theta is 0, the cosine of the angle is 1, and the intensity is unchanged by the second Polaroid. If, on the other hand, the two Polaroids are cross-polarized, with theta being 90 degrees, the intensity drops to 0 and no light is transmitted. The two Polaroids are placed on the two sides of a goniometer, a rotating device for measuring angles. The light source is placed on one side and the detector on the opposite side. Rotate the goniometer to tilt one Polaroid relative to the other, and measure the intensity at 0, 10 degrees, 20 degrees, etc. through 90 degrees. Since you're interested only in the angular dependence of the transmitted intensity rather than the absolute intensities, divide all intensities by the maximum intensity obtained with the angle at 0. Construct a plot of intensity versus the angle in degrees. Perform a curve fit of a cosine squared function with the angle converted to radians. Notice that we left a parameter b to account for the possibility that whoever mounted the two polarizers may not have aligned them perfectly when the goniometer reads 0 degrees. Note the value of this angle offset. Here we had negative 3.15 degrees. These results can be linearized if you plot intensity versus the squared cosine of the radian angle. The angle offset found above should be included, or the plot will not be a straight line. In this case, the correction amounted to adding the 3.15 degree offset to every angle. The plot of intensity versus cosine squared should be a straight line with a slope of 1. You will have shown from this result that the intensity of the light depends on the square of the electric field amplitude.